an associate professor in Department of Mechanical Engineering at IIT Bombay. He earned his PhD degree from Nanyang Technology University, Singapore in 2008. Before joining IIT Bombay in 2015, he worked as senior researcher at VTT Technology Research Center of Finland and as a postdoctoral fellow at Georgia Tech University. Professor Dixit has published over 75 peer-reviewed articles and currently serves as an associate editor for Microsystem Technologies and Scientific Reports. His research focuses on MEMS fabrication, 3D printing, through silicon wires, that is TSV, and micromachining of brittle materials used in semiconductor applications. With this short, brief introduction, I would like to invite Dr. Pradeep Dixit to deliver his talk. And now I hand over the sessions to Dr. Pradeep Dixit, sir. Dixit, sir, please.
Yes, thank you, Piyush. Okay, so
welcome.
So as Piyush has mentioned that I'm a faculty here in Department of Mechanical Engineering at IIT Bombay. And today I'm going to talk about something about micromachining process. So Piyush, just to save the bandwidth, I'm going to close my video, right? Okay. Is it all right?
Yes, yes.
Okay. So let me just share this screen. Please confirm whether you are able to.
If it is visible.
I'm going on slide mode. Okay. I believe that you are able to see that part, right?
Yes.
Okay.
Yes.
Okay, just to give me a minute. So I'm closing it, right? So yeah, fine. Okay, so a very warm welcome to all the participants. Okay, so today I'm going to talk about this micromachining of non-conductive materials, and these materials are going to be used in a semiconductor application, right? So most of the faculty members and participants who belong to mechanical engineering, we are quite familiar with the metal alloys micromachining process, right? But when we talk about these brittle materials, okay, typically the micromachining part of those things are often ignored, right? But thanks to all the activities which are happening in the semiconductor domain, okay, this particular area is becoming very important, okay? So let me first highlight a few things about in this particular domain. Okay, we just see. Okay, so all of you are probably able to see this particular map. Okay, so right now, thanks to the activity which is happening under the Indian Semiconductor Mission, okay, you can see that various microelectronics as well as the semiconductor packaging plants, okay, which are being set up across the various cities in India, okay, and Gujarat, of course, is taking a lead in that particular domain. So if you look at here, Gujarat right now is going to have about 5 semiconductor packaging related plants within India, okay. So Tata Electronics, we have a Micron, we have a Keynes, we have a CG Group, okay. These are all the 4 major electronic manufacturers which are setting up the plant activity in Gujarat. Okay. In addition to that, in Surat, you have a Suchi Semicon. Okay. In Ropar, we have the plant for AZIP. Similarly, there are 2 plants which are recently announced in state of Odisha. Okay. Similarly, in Assam, we have a lot of activities basically happening in the Tata Electronics thing. Okay, so these are some of the major companies which are going to set up their plants in that field, right? So when you look at this particular thing, it is very, very clear that in coming years, okay, we are going to see a lot of activities in this particular domain, okay, and this particular domain is going to require a huge demand of skilled personnel. Okay, so that is one of the tasks which we have. So now the question here is that whether our Indian academia is ready. So as a faculty member, those persons who are working in the academics area, right? What is our job? Our job is basically to provide the skilled personals which are going to be actually used in this particular domain called semiconductor packaging plant. Okay, and I'm going to highlight, okay, that when we hear this particular word called semiconductor packaging, typically we believe that this particular domain is about electronic industry, but not exactly. I would like to point out here that this particular domain is not only about electrical or electronic engineering, but also mechanical engineering can play a very critical role. Okay, so before we proceed, I want to highlight the very first question is that what exactly is this semiconductor packaging? What do you mean by that? Okay. So if I show you this picture, okay, this picture on the left hand side, it basically represents a 300 millimeter silicon wafer, which is being fabricated at a company called TSMC, Taiwan Semiconductor Manufacturing Corporation. And if you look at this particular thing here, this silicon wafer basically contains a lot of several identical dies. So for example, each square in this particular picture, whose enlarged view is shown in this diagram here. This is a die, okay, die of a microprocessor, same microprocessor which is being used in our computers, laptop, mobile phone also, right? This is basically the most important chip which you have in this part. Okay, so this is a silicon wafer, and this diagram here indicates about a particular chip. But when we look at from the end user point of view, okay, as a end user, okay, what we are familiar with something like this, right? So here, this is what we call as a packaged die. Okay, and if you look at the cross section of this particular package die, okay, it basically contains the same silicon die which is coming from this particular wafer, right? So on the left hand side, we have a silicon wafer, okay, and on the right hand side, we have something what we call as a packaged die, okay. So what exactly is semiconductor packaging? Semiconductor packaging is nothing but, okay, a transformation of a fully functional microprocessor wafer, okay, which may contain several of these particular die, and we need to basically convert this particular die in something like this, okay, right? So this one here, where my red pointer is pointing out, this is what we call as a packaged IC. So, okay, IC basically is a full form of integrated circuit. Okay, so if you look at this particular part, okay, what is the major function of the package die? Okay, this you can see that this is a metal cap. Okay, so metal cap basically is a kind of a protection of this IC wafer. Okay, so packaging basically provides some kind of mechanical protection from the ambient condition. Okay, we do not want that this particular silicon die is damaged because of the external conditions. Okay, those who are not familiar with this particular IC wafer, I like to point out that the thickness of this particular silicon die is only 50 micrometer, 50 micrometer. Okay, just to give a comparison, that our single human hair has a thickness of something about 80 micrometer. Okay, so it is thinner than of our single human hair. Okay, so that is one function. Okay, mechanical protection. And this particular package basically provides the interconnections. How do we basically provide the power from the external world to the ICs, and whatever is going to be the response of that particular IC, we need to take away the signal from that part. Okay, so all of these are going to be a function of a package, right? So electronic packaging or semiconductor packaging, which is called in general, it is basically a transformation of these individual dies into some kind of a packaged form. Okay, and that what exactly is going to happen in Indian semiconductor packaging plants. Okay, so if I show you a picture here, right? So on this picture, we are going to show you a very, very simple basic packaging process, And I'm going to highlight here that what are the important process steps which are going to be involved in this particular domain. Okay, so the motivation to share this particular slide is I want to highlight key what are the various skills which are going to be required in this particular part. Okay, so for example, companies like Kane Semiconductor, companies like CG Group, they are going to get a wafers, fully functional device wafer from companies like TSMC, or it is coming from Global Foundries or any other places, right? So the starting piece is going to be a fully functional 300 millimeter diameter wafer. Okay, and this wafer is going to contain a lot of multiple dies, right? So what we have to do, we have to first do some kind of a back grinding and polishing, and then we need to do something what you call as a dicing or sawing. Shaw. This is a wafer shaw. Basically, by using this kind of diamond blade, okay, we can break this particular silicon wafer into multiple dies. Okay, and from this step to this step, this is all going to be mechanical engineering alone. Okay, maybe because in mechanical engineering we are familiar with back grinding process, polishing process, right, dicing process, and so on. These are the some of the fundamental processes which we are learning in our mechanical engineering. Okay, so let's say that we have uh, reduced the thickness of the wafer, then we are going to have something like this. This is what you call as a lead frame. Okay, this is basically a kind of metal frame. Okay, these are manufactured by various companies. Okay, so let's say that we have a lead frame. What we are going to do, we are going to put this particular silicon die, okay, on top of the substrate lead frame. Okay, right? So this particular process is going to be achieved by using some kind of a glue adhesive. Okay, again, this is a mechanical engineering alone. Okay, we want to ensure that this particular silicon die does not move. Okay, it stay on a particular place. Okay, afterwards, as you can see that this is a lead frame, which is going to be metal frame. Okay, we need to provide electrical interconnection between the silicon die. Okay, so it is not very clear in this particular picture, but here on the periphery where we have some kind of yellow part. Okay, so each of these lead frame are going to be attached by a very tiny wire. Okay, these wires are basically gold wire, real gold. Okay, so by making the proper connection between a silicon die to lead frame, we can provide a electrical interconnection. Okay, that means that the whatever is going to be the response of this particular silicon die, that response is going to be transferred to this particular part. Okay, so that is again, so wire bonding. Okay, if you look go in little bit fundamentals of wire bonding, it is nothing but a micro welding. Okay, most of the mechanical engineering guys, okay, we are all familiar with the welding process. This is exactly a micro welding process where we need to provide metal to metal connection between the lead frame. On one side we are going to have the connection at the die. Okay, so again, welding knowledge is well familiar to all the mechanical engineering. This is what we are going to do. Okay, then the process, once we have established electrical interconnection, we need to go for molding process. This is basically a injection molding process where the top side and bottom side is going to be fully covered with some kind of a polymer epoxy. Okay, again, fundamentals of injection molding is well familiar. This is what the companies are going to do. Okay, and then we are going to do some kind of marking, plating, electroplating, and so on. So this is kind of a process flow which basically is going to be performed at various semiconductor packaging plant. Okay, so now the motivation what I like to point out here, if you want to look at this particular packaging process flow, okay, we do not require any electrical engineering. Electrical engineering, electronics engineering, whatever is going to be needed, that is basically at this particular stage. In fact, that one is for the design purpose only. Once the fabrication or manufacturing is going to start, okay, we would be requiring the knowledge of mechanical engineering. Okay, for example, back grinding, polishing, okay, micro welding process, injection molding and process. Okay, we require a lot of knowledge on the material science, that what should be the epoxy material, right? What should be the interconnection material, how we can basically improve the performance of those things. Okay, so materials is going to be very, very important in the semiconductor packaging. Similarly, the knowledge of chemical engineering, okay, basic fundamental physics, numerical simulations, design of experiments, quality control. Okay, these are some of the basic fundamental skills which are going to be required at various semiconductor packaging plant. Okay, so the very common perception which we have, that when we talk about semiconductor packaging, we feel that, oh, this is not an area of mechanical engineering, we should not be bothered about that. That particular perception is not really correct. Okay, and that's why when you look at the requirement of skilled manpower, okay, all these companies are going to require a lot of material scientists. Okay, they require mechanical engineering, chemical engineering. Okay, those guys which who are familiar with quality control, DOE, and so on. Okay, so if I go a little bit uh, detail about the cross section of the package or semiconductor package, okay, this is how it looks like. Okay, so this is a very simple cross sectional image of a semiconductor packaging. So here we have ICs, okay, integrated circuit, okay, and these ICs are going to be mounted on a substrate. Okay, so these balls which are going to point out, these are the solder alloys. Okay, so again, in mechanical engineering, okay, many of us are familiar with the soldering and brazing. Okay, this is exactly the same solder which we are familiar with that. The only difference is that the size of these solder balls are typically about 20 micrometer, 30 micrometer. Okay, so from our conventional mechanical engineering, when we talk about semiconductor packaging, okay, the major difference comes in the domain of size. Okay, so in mechanical engineering we are talking about something about millimeter size. Okay, in semiconductor we are talking about like tens of micrometer in that way. Okay, so if you look at this beautiful picture, okay, we require basically the first step in any semiconductor packaging is going to be design, right? So when you talk about design, it's not only about electrical design, right? Electrical engineering, electronics engineering guys, they are going to decide that what should be the dimension of interconnections. Okay, but overall, if you look at this picture here, we require the design, optimal design from thermal point of view. Okay, from the mechanical point of view, we would want to create a very reliable product. So we need to basically think about from the thermal point of view. Now, most of you are familiar with the electronic devices, right? So whenever we are using any our phones or tablets or computer, you might have noticed that if you keep on using for let's say certain like minutes, right, or few hours, you will see that most of the electronic devices are now basically heated up very quickly. Okay, and because of the temperature, okay, heat dissipation, okay, is one of the major problem. Okay, most of the electronic devices when they are failing, okay, thermal related issues is one of the major concern that, and that's why when we talk about this kind of semiconductor packaging, okay, we have to be think about from the thermal point of view. Okay, similarly, materials, like I said, are going to be very important, and this is where I like to stress a very important point, right? So in mechanical engineering, when we talk about material science, okay, most of the mechanical engineering faculty members, okay, and also students, okay, they do not put a lot of efforts in learning about the material science. They feel that material science is about iron carbon diagram, right, steel and so on. Okay, but that's not really a very complete picture. Okay, materials are going to be the most critical part of a semiconductor package. Okay, and this is where I like to request all of the faculty colleague, okay, that please think beyond metals and metal alloys. Okay, so polymers are going to be very, very critical part. Okay, so if you look at this particular package here, okay, this one package is typically about this could be a printed circuit board, okay, or this could be, for example, a silicon material. It could be for example, glass-based material, alumina-based material, and so on, right? So these materials are typically brittle in nature, right? Most of the ceramics, for example, if you look at here, they are all going to be brittle in this part. Okay, this dark side, the black color which I'm pointing out here, they are polymers. Okay, their basically objective is to provide a electrical isolation. Okay, and this blue line here, which is showing here, for example, they are what we call as a interconnection line, and they are typically made out of metal. Okay, so for all these advanced semiconductor packages, okay, if you want to make a reliable part, we need not only we have to worry about the metals but also polymers. Okay, similarly, these solder joints, okay, they are typically a alloy, right? Most of the time we are using tin based material and so on. Okay, so my message here is that, okay, that although we are from mechanical engineering domain, okay, we have to have a very strong motivation to learn about the basic material science. Okay, especially when the dimension of these materials are basically in few micrometer. So fundamental mechanical properties, material properties, even thermal properties are going to be drastically different. Okay, so we need to motivate our students to learn about material science. Okay, that's very critical part here. Similarly, when we talk about making all those process steps, okay, this is what we call it, comes under the processing side. Okay, so we have various process steps. For example, lithography, we have a thin film deposition process, we have a etching process or material removal process, and so on. And they are basically similar to what we are doing in our mechanical engineering, but the difference is basically on the dimension part here. Okay, finally, once you complete this thing, okay, all these electronic packages goes under the testing, measurement of various properties, quality, control, reliability. Okay. Okay. So when you look at, for example, this particular area, okay, we not only require electrical engineering, okay, we require material science, mechanical engineering, we have a chemical engineering, we have physics knowledge, okay. We need, for example, artificial intelligence also, machine learning also, to find out what is going to be the defect in a particular wafer. Okay, because wafer size is going to be very large. Okay, and they will come thousands of such kind of dies. Okay, so when we want to find out that how many dies are going to be present and how many dies are going to be defective, okay, that is going to be involved a lot of data. Okay, so we need to find out, okay, that which particular die is defective. Okay, what is the pattern of the defective dies across a particular wafer. Okay, so that is going to require advanced knowledge and so on. Okay, so I hope that I have given this particular message that in this particular domain, we require multiple engineering discipline knowledge. And this is a truly interdisciplinary domain here. Okay. So now let me talk about, so if you look at, for example, this kind of a package here, as I mentioned, okay, that this IC wafer, they are silicon. Okay, so silicon is basically also a kind of brittle material. Okay, similarly, the ceramics, glass based material, whatever we are going to use, okay, they are also belong to brittle material category. Okay, so when we talk about creating these features, this kind of micro features in brittle material, okay, it is going to be a challenging task. Okay, so here we have a slide. Okay, and this slide basically tells you, okay, that how we can use glass based material, okay, in various semiconductor packaging application. Okay, so remember that glass is a very fundamental basic word, okay, which is basically representative of silicon and oxide. Okay, so when I talk about glass, okay, in pure form, it is basically a kind of ceramic made out of a silicon, okay, and oxygen. But depending upon what kind of glass we are talking about, sometimes metallic impurities like boron, soda, for example, sodium, okay, they are also added. That's why in market we have a borosilicate glass, we have a soda lime glass, we have a quartz also. We have a kind of a various different forms are going to be present here. Okay. So let's discuss a little bit of the glass, okay, and what are the advantage here, right? So when you look at, for example, those who are familiar with the little bit of the silicon, okay, silicon is a semiconductor material, right? Because it has a outer electron, it has outer shell, it has a 4 electrons, okay. So this is a semiconductor category, but glass or silicon oxide, this is a perfect insulator, right? So silicon being a semiconductor, its electrical insulation characteristics is not very good, but glass is a very good electrical resistivity. So if you look at the resistivity of glass, okay, that is 10 to the power 14 ohm meter. Okay, So compared to silicon based material, it has a very, very good thing. Okay. It has a very low dielectric constant. Okay. So in our class 12th, most of us have gone through something called dielectric constant. Okay. And this dielectric constant for electrical transmission point of view, okay, it is preferred to use a low dielectric constant because that basically decide what is going to be the signal speed. Okay. So glass basically has a lower dielectric constant. Glass is a very good having a very good chemical resistance. So for example, you might have seen that in our laboratory application, right? In our daily life also, okay, even sulfuric acid, hydrochloric acid, nitric acid, okay, they're all stored in a glass bottle, right? So glass is not being affected by this kind of strong acid. So it has a very, very good chemical resistance. Okay. If you look at the melting point, okay, glass has a melting point of 1400 degrees Celsius plus. So it means that if you are making any kind of devices from the glass, okay, that particular glass can be exposed to high temperature also. So up to 1400 degrees Celsius is not going to be affected. Okay. And best thing is that, okay, glass is an optically transparent material. Okay. So it means that if you want to observe that what kind of processes which are going to happen, okay, that from that point of view, it is going to be very good. So these are some of the critical material properties of glass based material. And because of these particular properties, okay, you can see that glass is being used for many of the microfluidics application. So for example, these two chips, you can see, okay, that okay, this is basically example of a lab on a chip kind of application. Okay, so here where my red pointer is pointing out, okay, this is a basically kind of input here. Okay, and this is going to be output. So here you can attach some kind of let's say fluid, and that particular fluid is going to be distributed across this particular world. Okay, so in this example of these microfluidic devices, okay, people are using glass substrate, okay, so that they can really monitor what is going to, what kind of chemical reaction is happening here. Okay, so it's going to be there. Similarly, because of the superior electrical insulation properties and low dielectric constant, glass is also being used in various semiconductor packaging application, and that's what we are going to talk about in today's lecture. Okay. So idea here is that we know that we are going to have a lot of this kind of interest. Okay. And one of the motivation, one of the very recent development which has happened. Okay. So this particular development is shown in this particular slide. Okay. So what you are looking at on this particular slide here. So this is a Intel engineer. Okay. And if you look at, for example, this is a glass panel. Okay. This glass panel is about 2 feet in size. So this is a 600 millimeter by 600 millimeter square panel. Okay. And the thickness of this particular glass panel is only 1 millimeter. Okay. So you can imagine only 1 millimeter thick glass panel having a size of 600 millimeter by 600 millimeter. And each, if you look at, for example, closely in this picture here, you can see we have various squares, right? And if you look at closely, okay, each of these square, they are going to have multiple thousands of the through holes. Okay, so for example, if you look at my pointer here, okay, this basically shows you a glass panel which are having through holes having a size of 75 micrometer is the pitch size. So when you look at, for example, the distance between the two through holes is only 75 micrometer. Okay. And the white color here indicates is a copper. Okay. So basically the idea here is that for the advanced semiconductor packaging application, okay, companies like Intel, they are using this kind of a glass panel. Okay. And this glass panel contains several tens of thousands through holes which are filled by the electroplated copper. So for example, this white color here, this is going to be copper, and the dark color basically represent about the glass substrate. Okay. So this kind of development is happening, and Intel has last year, they have basically opened a first foundry, which is basically based on the glass panel part. Okay, so we have a lot of interest in the glass substrate, and various companies are going to open up this plant here. In fact, in India, in Odisha, okay, there's a company called 3D Glass Solutions. Okay, three-dimensional glass solution. They are creating these advanced components which are embedded in the glass substrate itself. Okay, so they are basically looking forward for very hiring various engineers and so on in this particular domain. Okay, now the question here is that, okay, when we talk, the question is that how do we create such kind of a tiny microstructures, right? Those microstructure could be a blind via, could be through holes vias, it could be some kind of micro channels, right? Okay, so dimension of those microstructures could be anything from 20 micrometer onwards. Okay, so question comes that what are the existing techniques which can be used for glass-based material. Now we already know that the techniques, for example, micro milling, micro drilling, which we typically use in our mechanical engineering, okay, those techniques are not going to be helpful because the moment they are going to touch any kind of mechanical force, okay, glass being a brittle material, it is going to be broken very quickly. Okay, so what are the ways? Okay, so the industry is relying heavily on the laser ablation process. Okay, they are using a laser ablation or laser assisted chemical etching process to create this kind of feature. Okay, so there are two techniques. One is what laser ablation, where they are using pure laser, okay, to raise the temperature beyond the vaporization temperature. That's one technique. Okay, but if you look at, for example, this technique here, okay, this is a very costly process. So for example, the femtosecond laser which are being used for glass-based material, it easily costs something about 5 crore plus. Okay, and that's why if you look at Indian context, okay, we don't see many femtosecond laser available across India. Okay, then we have some technique called plasma etching process. Okay, but it has an extremely slow etch rate. We can use wet chemical etching. Okay, so in the beginning I mentioned that glass has a very good chemical resistance with sulfuric acid or nitric acid, even hydrochloric acid. But if you use hydrofluoric acid, okay, glass can only be etched by hydrofluoric acid. Okay, so the people can use this particular technique, but it cannot create a very deep structure. Okay, so although industry is heavily relying on the laser based process, okay, but as I said that this is expensive process, and especially from the academia point of view, okay, may not many institutes they have a direct access to this particular process. Okay, so what we have tried to do here in IIT Bombay, okay, and other institute also in India, okay, we have developed a couple of processes, and one of the processes is called electrochemical discharge machining process, which I'm going to talk about today. Okay, so in IIT Bombay, my research group has also worked in the ultrasonic micromachining process to create a process which can be used for as a kind of a cost effective alternative to laser ablation or laser assisted chemical etching process. Okay, so what is our approach? Let me show you. So if you look at this picture here, right? So ultimately, okay, our idea was that we would like to create this kind of a device, right? Now, this particular device, those who may not be familiar with this electrical design, this is nothing but a kind of inductor, right? So we have a glass-based substrate, okay? The thickness of this particular glass is roughly about a millimeter thickness, okay? And if you look at this particular maroon color, this is basically a indicator of the copper. So for example, if you put two electrical probes, right? Let's say that this is input, so electrical signal is going to be coming here. It is going to be like moving. It is going to go from the top side to back side. Okay. And here we have the backside interconnection, and then it is going to come away. Okay. So this is like a kind of a looped kind of structure, which is also known as a inductor devices. Okay. And inductors are a component, basic component, which basically stored electrical engineering under the magnetic field. So if you recall in our older days, right, in our tube lights, we used to have this kind of choke. Okay, so choke is nothing but kind of inductor one. Okay, so this was kind of a idea we wanted to try. And if you look at the process flow, so this is a kind of a glass based material. So we wanted to create the, if you look at this diagram here, so we took a kind of a glass based substrate, or it could be aluminum substrate also. So we can basically create some kind of lines. If you look at the structure here, they basically represents the structure which is going to be there. Then the next step is going to create this kind of through holes, and later we can basically fill these structures by electroplated copper, right? So there are two processes which are going to be very critical in this particular thing. One is what we call as a microstructure formation, and for that we have two techniques which we have developed at IIT Bombay. One is what we call as a electrochemical discharge machining process, and second one is what we call as a ultrasonic micromachining process. Okay, so so that's the first thing. Second thing is that how do we fill those structures with electroplated copper, and for that we have been working, and we have a technique called electroplating, okay, about which we are going to talk about now. Okay, so there are two techniques. Okay, so I'm going to talk about the first technique, which is what we call as a electrochemical discharge machining. Okay, some of you might have heard about this particular technique. Okay, so when we talk about electrochemical discharge, okay, this technique is basically a combination of electrochemical machining and electro discharge machining. Okay, in our mechanical engineering, most of the faculty members and student, you might have gone through ECM and EDM, right? So ECM and EDM both are used for a electrically conductive materials. Okay, but electrochemical discharge machining can be used for a non-conductive materials. Okay, so idea is that it's a very, very simple process. Okay, so let me first show you the basic fundamental here. Okay, so what we are having, so so we have a glass based sample. Please remember that glass is a non-conductive material, so it means that I cannot connect to any polarity. Okay, so let's say that I want to create some kind of a through holes or some kind of a channel. Okay, so we will be requiring some kind of a conductive tool. Okay, so we have a tool here, and then we are going to have a large counter electrode. So surface area of this counter electrode has to be much larger compared to the tool electrode. Okay, and then we have this kind of a machining chamber, and we will is going to fill with electrolyte. Okay, so this electrolyte has to be a alkaline medium. That is very, very important. Okay, it cannot be a salt electrolyte, it cannot be a acidic medium, it has to be basic or alkaline medium. Okay, why is that? Because this process, okay, the material removal is also taking place because of the chemical action. Okay, so what happens is that, so once you have some kind of, let's say, sodium hydroxide or potassium hydroxide, okay, along with water, okay, and when you connect this particular polarity here, what happens here, that the water which is going to be present in electrolyte, it will go under electrolysis. Okay, so H2O is going to basically break it down, it will give you H plus, and H plus is going to come towards the tool, because tool is going to be negative polarity here. Okay, so at this particular phase here, okay, so what is going, because this is going to be a negative electron source, H plus is going to convert into H2, basically hydrogen gas bubble. Okay, so slowly what is going to happen here, okay, near the tool electrode, we are going to have a hydrogen gas film which is going to be created. Okay, so up to this particular stage, when where the water is going under electrolysis and creating a thin film of hydrogen, we are following the fundamental of electrochemical process. Okay, now if you recall EDM, right, electro discharge machining process, so you can imagine, if you look at this particular picture here where I'm pointing out right now, we have a conductive tool. Okay, we have a conductive electrolyte. Okay, and in between we have a non-conductive hydrogen gas film. Okay, So if you increase the voltage, I'm sorry, if you increase the voltage, depending upon what is the thickness of this hydrogen gas film, okay? So what, okay? So once the applied electric field goes beyond the breakdown strength of this hydrogen gas film, okay, right? So when applied electric field, which is going to be E, is going to greater than breakdown strength, this hydrogen gas film is going to break down, okay, and discharge process is going to start, okay, and this discharge is going to fall on the glass sample, which is kept very close to the tool electrode. The gap between the tool and the glass workpiece is roughly about 10 to 20 micrometer only. Okay, so whatever is going to be the discharge energy, because of that particular discharge energy, what will happen that the temperature of that particular surface on the glass is going to go up. Okay, so typically it is going to be heated up something about 1000 degrees Celsius, 1500 degrees Celsius, 2000 degrees Celsius, this some kind of range. Okay, so when it happened, there are two mechanisms. The mechanism is going to be localized melting and vaporization process because of the heating. Okay, so as we have said that depending upon what kind of glass you have, okay, if the temperature is going beyond the 1500 1600 degrees Celsius, we are going to have a melting. Okay, but more importantly, what is going to happen here, that we are going to have temperature assisted chemical etching. Okay, so when the glass becomes soft, okay, the etching rate of the alkaline medium, okay, with, so alkaline medium is going to react with glass and it is going to create sodium or potassium silicate. And this particular reaction is having a very significant contribution when the temperature on the glass becomes more than 700 degrees Celsius, right? So I hope that all the faculty members are going to follow this particular thing, okay, that in ECDM, okay, the majority of the material removal is basically happening because of this particular phenomena, okay. So that's why this particular term is used called temperature assisted chemical etching. And that's why I said, okay, that the electrolyte, which is whatever we are using it here, it has to be a alkaline medium. Okay, if you use salt electrolyte or if you use an acidic medium, this reaction is not going to take place. Okay, and that's why you will not find any uses of acidic electrolyte in the process here. Okay, this is one of the real picture of our setup. So we have a tool electrode here. We are using 3x3 array tool. This is a counter electrode. Okay, and you can see very close to here, you can have a very localized discharge. Okay, and this discharge is basically causing this particular glass piece of sample is going to fault. Okay, so if I go a little bit more in depth, okay, these are the some of the critical stages which I have highlighted here. So this is the tool electrode. Okay, and when you apply, for example, voltage, okay, you can see that we have hydrogen gas bubbles which are going to be created. Okay, and so after some point of a time, these hydrogen gas film, they are going to basically will create some kind of a gas film. Okay, and later on this particular gas film is going to discharge. So we have a localized discharge, okay, which is shown here in white color. Okay, and because of this particular discharge, that the temperature on the glass piece is going to go up and so on. Okay, so there are two important things. Okay, that material removal is happening mainly because of the temperature assisted chemical etching. Okay, and now if you want to basically achieve a high temperature, you need to keep the sample very close to the tool. That's why I said the gap between the tool and glass sample is very, very critical. Okay, so as per our research, it has to be less than 20 micrometer. Okay, if the gap is going to be very large, what is going to happen here? Okay, if I go back, for example, if the gap is going to be here, okay, because of the discharge energy, okay, energy is going to be there, but if that this gap is going to be large, the surface temperature will not reach up and the chemical assisted etching is not going to take place. Fine. So I hope that, okay, so here is just a picture of our setup. Okay, so you can see that. So we have built up this particular kind of 3-axis machining chamber. Okay, so we have this machining chamber here which can move in X and Y. and then we have the z-axis which can go up and down, right? So this is a 3-axis kind of a process, and you can see some of the images here. The important components in this particular whole setup is the power supply. Okay, the power supply is the most expensive component. If any one of the faculty member is basically like to know more about that, then you can always contact me separately. Okay, and we are going to talk about this process here. Okay, so you can see that this is kind of process is very dynamic here. Okay, some kind of high speed camera. You can see that this is a real image here. Okay. So, okay, so as I said that similar kind of activities is also happening in other institute. Okay, for example, IIT Roorkee has a very strong group. Okay, also Punjab Engineering College have some activity. Okay, and also some other universities also which are working on that particular domain. But in how IIT Bombay research work is different. Okay, so as per what our research, we are the only group in the, I would say, in the entire world, to the best of our knowledge. Okay, so our work is basically using the this kind of a multi-tip electrode. If you look at other researchers, okay, they are using a single tip electrode. So our idea here is that, okay, that by using the wire iridium process, we are able to create customized tool electrode. So for example, okay, you can see that we can create this kind of a tool tip 5 by 5 array. So 1, 2, 3, 4, 5 on X, 5 on the side. We can also go for 8 by 8 arrays, or okay, 2 by 5 array, and so on. Okay, so by using the wire iridium process, we can basically fabricate a customized tool electrode. Okay, and then particular tool electrode can be used to create the opening size in the glass based material. Okay, so when you look at, for example, the tool tip size, the finest tip size which we are able to create in our lab by using the wire iridium process is 150 micrometer. Okay, so it means that if I use this particular tip electrode, the size which we are going to get in glass, it is going to be more than 150. So typically about 200 micrometer plus or even more, we are able to create on the glass based material. Okay, so entire glass based material, this is going to be on about SS material here. And if I show you, of course, this is a these results are basically about the overall work of more than for 5 years. Okay, so if I can show you the final picture here, so you can see that we have a 2-inch substrate out of a glass-based material, and you can see that they're all basically going to be through holes here, right? So through holes are going to be created. Okay, we can, using the customized tool electrode, we can create all kind of various through holes in this particular aspect one. Okay. If you have any questions, maybe you can start sending those questions by the chat option, and at the end of the presentation, I'm going to handle those questions. Okay. So if you look at this process here, okay, this process can also be applied not only for making the holes, okay, but you can, depending upon how you are moving the tool electrode. Okay, so as I already told you that we have a 3-axis machine. Okay, so you can basically bring the tool towards the z-axis for making the drilling. Okay, or you can basically move in X or Y motion, and then you can create this kind of a part here. Okay, so you can see that, for example, if you want to as a milling application, if you want to create a deeper channel, okay, so you can go for a multi-pass approach. For example, first pass is roughly about 80 to 100 micrometer. Okay, you can go for 2, 3, 4 passes, and you can create a very kind of a deep structure in this particular way. Okay, so this process can be used a single tip, and then let me show you also. This is one of the work which we have done it to create a micro fuel cell. Okay, so this is one of the DST project which on which we have created this kind of multiple this kind of micro channels. Okay, so you can see that this is 1, 2, up to 18 micro channels are there, and these channels were basically used to create all this kind of a channel here. Okay, so now let me just show you one thing here. Let me just okay. Hopefully this should work, right? So just to show you the kind of a proof of concept kind of application. Okay, this is just one demo purpose here. So this is basically a kind of lab on a chip application. So we have a 2 glass slides. Okay, and in one glass slide we have created this kind of a blind channel. Okay, let me show you one picture, one video. Please pay attention. Okay, so what we are doing is that this is one reservoir. Okay, That is the output. And we have created this kind of micro channel, and we are simply dropping a colored ink. Okay, and let me show you. Okay, hopefully this works. So you can see that. Okay. Now you can see that, okay, this ink is basically following through the micro, this kind of channel. Okay. And we do not have any pressurized flow. It is just atmospheric pressure. Okay. You can say that amount of the ink is going to be reduced here. And in the beginning, the flow was very fast. But since we do not have any kind of pressure here, it is going to gradually, it is going to grow slow like this. Okay, and you can see that. So from this to this, it takes roughly about 50 seconds roughly to reach there. If you can include, if you can provide some kind of precise flow, okay, then you can do that, this kind of part. So this is just kind of a demo that that potentially this particular technique can be used to provide some kind of lab on a chip kind of application. Okay, that's what we have tried to do that. Okay. So, so if you look at this technique, okay, this technique was very good, but only it has a one problem, okay, because the fundamental material removal is basically dependent on the temperature, right? And we need to produce a temperature of something about 1500 degrees Celsius plus. And because of the high temperature usage, the tool tips, okay, it has a very I would say high tool wear because SS material is being used, and as you know from the basic knowledge, okay, that when this discharge is going to be created, okay, the tool tips also become soft. Okay, most of the metals have this particular characteristics because of hot hardness feature. Okay, so we were basically wondering that whether we can have a alternative process which can be used for a room temperature machining. Okay, and that's where we started working on this kind of a process called abrasive based ultrasonic micromachining process. Okay, so the concept was basically the same. Okay, let me just point out. Okay, so you can see that the same tool tips, same kind of tools were also used in ultrasonic machining process. The fundamentals were same, whatever we have learned so far in our mechanical engineering. So idea here is that we have a glass based material, right? And we have this particular tool, and the tool is basically vibrating. Okay, so tool is kind of vibrating at a very high frequency, more than 20 kilohertz, and the vibration amplitude is roughly about 10 micrometer. Okay, so those who are familiar with the ultrasonic micromachining process, let me just show that. So idea here is that very simple. So we have a tool, and tool is vibrating, okay, at a very high frequency, but amplitude is very small. And in between tool and workpiece, we are providing some kind of slurry. Okay, slurry is basically nothing but abrasive silicon carbide particles. Okay, having size typically about 1 micrometer to 10 micrometer, what we are using it. So what happens is that when the tool is vibrating like that, okay, the tool pushes the whole part, which is going to be slurry, okay, and this tool provides certain kind of direction, okay, towards the downward direction, right? So, so if you look at individually a single particle, okay, of course, in this diagram, I have chosen a sphere, okay, but in actual case of ultrasonic, okay, the abrasive particle size is going to be totally random, okay. So what is going to happen here that the ultrasonic vibration is going to provide certain kind of velocity, right? So if you know, for example, let's assume that we have a sine wave, y is equal to a sine omega t. So you can do a differentiation and you can find out what is going to be the velocity of this particular tool. And if we assume that the same velocity is also being transferred to the abrasive particle, so what is going to happen here? That this particular abrasive particle, which will have certain mass, okay, and because of the vibration speed, it is going to have certain velocity. It means that it will have certain kinetic energy, right? So let's assume that we have a kinetic energy of half mv square, and when it's going to hit the sphere, this particular glass based material, it is going to transfer the entire kinetic energy to this part here. And if the resultant forces on this particular glass is going to be more than the fracture strength, okay, we are going to have certain kind of a fracture point here, okay, and as a fracture, this part is going to be kind of over. So this is a kind of basic fundamental of the ultrasonic micromachining process. Okay. So what we have done it, of course, maybe because of the time, I will not go in but bit detail, but let me just indicate here that whoever is working on ultrasonic micromachining process, right? One of the first thing which you have to do is to do this kind of a numerical analysis of the horn design, right? So this is basically horn, okay? This is the from this part, okay? Beyond this part is going to be the tool, and this is going to be known as a horn. And objective of the horn is basically to amplify whatever is going to be the vibration which you are receiving from a piezoelectric transducer. Okay, so I will not go in detail because of the limited time which we have. Okay, if time permits, I will come back on this particular point later on. Okay, but idea here is that, okay, we have obtained a particular horn length. Okay, which basically ensure that we are getting the maximum possible vibration amplitude at the end of the tool electrode. Okay, then my student, they have also performed this kind of a basic finite element analysis to find out, okay, that what is going to be the approximate the material removal at the various input parameters, right? So here is just one example that we have a abrasive particle, okay, and when this abrasive particle is basically hitting with certain velocity, okay, it is going to create kind of a certain very small amplitude of the material removal. So in case of ultrasonic micromachining, material is being removed because of the continuous bombardment of those abrasive particles. Okay. So here the idea here is that we have to apply the forces in such a way that under a localized condition, the stress has to be greater than the fracture strength of that particular glass-based material. Okay. And how you can basically improve it or increase it. So you have two parameter. You can basically play around with the ultrasonic amplitude that is directly going to influence about the velocity and thus the kinetic energy, right? Or you can change with the abrasive particle. So if, for example, if you use 1 micrometer particle versus 10 micrometer particle, so as you know that 10 micrometer particle, it is going to be more heavy. Okay, heavy means that when it is going to strike the glass-based material, it is going to have the higher kinetic energy. So material removal, it is going to be a little bit more than that. Okay, so that's what we have done it. Basically, we have done both numerical as well as the experimental analysis. So here, basically, some of the basic fundamental graph. This is going to be power rating versus the depth. Okay, and feed rate versus the depth. So as expected that when you go for a higher amount of USM power, okay, then that basically result into higher amount of velocity. That means the higher amount of kinetic energy, and that typically means that higher material removal process. Okay. So if you, from the material removal point of view, we basically recommend higher USM power and larger abrasive particle size. Okay, but if you use a larger abrasive, then of course the roughness of the side walls of, okay, that is also going to be more. Okay, so you need to find out a balance between the side wall roughness versus the USM power and abrasive particle size. Okay. So here are some more kind of results indicating the same thing. So those faculty members who like to know more about that, here is the details about. So many of these results have been published in Journal of Manufacturing Processes in 2002. If you want, I can also share the copy of that particular paper later on. Okay, so here is kind of a combined results. So you can see that. Okay. So the top picture A, B, and C, they basically represent about the glass-based material. And as you can see that the glass material is about 1.1 millimeter thickness. Okay. And if you look at the opening size, we have a 270 micrometer. Okay. Bottom size is going to be 180 micrometer. So we are always going to have certain kind of tapering. Okay. Because of the two things. So if you look at the tool electrode which we are using it, they're also tapered. So that's one reason. Second thing is that when the material removal is trying to come out, okay, because of the coming out of this thing, the opening size is always going to be a little bit more compared to the bottom opening. Okay, so these are the kind of things. The important thing which I want to highlight here, that 1 millimeter thick glass, okay, was machined in less than 3 minutes. Okay, so compared to other processes which are being used in semiconductor application, this particular process is very fast. The only limitation what it has, that the opening size is typically large. Okay, 270 micrometer. Okay, And the reason behind this large opening is that the tool which we are using it, okay, they themselves are larger. Okay, so if we can create certain kind of smaller tip size, then it is possible to, create very small openings in the glass based material. Okay, similarly, this one, the bottom picture, they are on silicon. Okay, so you can see that, for example, they're all basically through holes which are basically created in this particular part. Okay, so all material, brittle material, silicon, fused silica. We have also able to machine alumina, which is typically quite difficult material to be etched. So let me show you. Okay, these are the kind of a part, and you can see that. Okay, so this is the opening, and if you look at closely, okay, we are going to have this particular side wall. Okay, and those faculty member who are interested, this picture basically represent about the abrasive particle size. Okay, so these abrasive particles are basically a kind of random size here. Okay, so typical average size what we are using in our lab is about, average size is roughly about 1 to 2 micrometer, and that's why if you look at the sidewall roughness, okay, they are less than 1 micrometer here. Okay, please remember that because this is abrasive based process, we are using silicon carbide as abrasive, and these silicon carbides also going to affect, okay, they are also going to create certain kind of tool wear on the tools also. Okay, so after for example 15 millimeter, if so, this is just a rough data. So we are able to use this particular tools up to 15 millimeter of glass. Okay, and during that particular process, okay, 1 millimeter tool was also worn out. So typically the tool wear ratio is 15 to 1. Okay, so that means that, okay, the glass machining rate is about 15 times faster compared to the tool wear rate. Okay, these are the results of alumina. Okay, those faculty member who might be familiar with alumina, right? Alumina is quite difficult material to work with. Okay, in semiconductor application, alumina has one advantage. As you know that alumina can withstand a very high temperature, something about 2800 degrees Celsius plus. Okay, and compared to glass, alumina is also a thermally conductive material. Okay, the thermal conductivity of alumina is better than glass. So roughly about 20 watt per meter Kelvin is the thermal conductivity. And because of this better thermal conductivity, alumina is going to be used for applications involving high temperature. For example, in power electronics, okay, in electric, this EV charger, electrical vehicle charging station, okay, many of the electronic devices are based on the aluminum oxide or aluminum nitride. Okay, so for those application, people are would like to develop these micro machining process for alumina, and this is where our results are. Okay, so for example, we can create. Okay, this is about 1 millimeter thick alumina. We are also able to create the vias in a 3 millimeter thick alumina also. Okay, and you can see that this is all going to be something like a through holes having a size of less than 300 micrometer and so on. Okay, so the message here is that, okay, even in a sintered alumina, which is a I would say a difficult to machine material, by using ultrasonic micromachining process, it is possible to create this kind of through holes without any kind of a problem. Okay, right? And compared to ECDM process, okay, ultrasonic micromachining process is a room temperature process. So it means that we don't have to worry about any kind of a thermomechanical stresses, right? Even the tool wear is much uniform compared to ECDM process, okay? And process has much more control compared to other processes, okay? So now, if once we have created this kind of via formation, okay, second step was basically about how do we deposit the metal inside these cavities. So for example, if you look at this part here, okay, remember that this is a alumina picture here. Our ultimate goal was to deposit electroplated copper in these tiny holes, right? So that we can use this particular die or chip for some kind of a packaging application. Okay, but okay, so in MEMS industries, in silicon micro fabrication industry, okay, whenever we want to deposit metal, typically we use electroplating, okay, and for electroplating we requires a conductive surface, but glass, alumina, they're all basically non-conductive surface, okay. So the first task, the first step for us was to deposit a electroless deposition process, okay. Once again, those who may not be familiar with the electroless, okay, okay. So if you look at, for example, in our many of our applications in daily life, we use this electroless process extensively, okay. So sometimes you might have seen that you have a plastic surface which is very shiny, okay. So what we do, we deposit a very thin layer of metal, typically either nickel or chromium, on those plastics, okay. And the method to deposit those thin layers is electroless, okay. So electroless basically is a pure chemistry based process where we are not applying any external electric field, okay. That's why the word electroless, okay. We are not applying any power, okay, battery power, okay. We just, this is just based on the chemistry alone, okay. So I will not, again I will not go in detail, but these are the some of the basic steps which are going to involve. So first we take these samples, whether it's a glass sample or alumina sample or polymers, plastic, whatever. First we do some kind of cleaning, then we go for a sensitization steps where we deposit tin chloride, okay. And this tin chloride basically result into tin 2 plus, which is going to be deposit on the surface. And after that, we perform something what we call as an activation or catalyst activation. Okay, this is the most critical step in electroless deposition method. And that basically ensure that on the surface, we have the palladium 2 plus. Okay, and palladium basically works as a catalyst process. And on that, we can deposit this kind of a tin-based material. Okay. So in our lab, one of my student, he has developed this particular process. Okay. So idea here is that, okay, if you look at, for example, glass-based material, okay, we can provide some kind of a local roughening. Okay. So this local roughening can be done either by the electrochemical discharge process or by the ultrasonic micromachining. Both of these techniques I have basically discussed so far. Okay. So idea behind using this thing, that if you can create any localized mechanical roughening, okay, that basically result into a very good adhesion between the electroless layer and the surface. So for example, if you look at this picture here, so you take a glass substrate or alumina substrate, you create local roughening, okay, then you deposit the electroless seed layer, okay. On top of that, you can deposit electroplating, okay. And if you perform any kind of, let's say, a peel test, you will see that because of this local roughening, okay, the adhesion between the electroless and the surface has to be very, very good. Okay, that's what our results basically clearly indicate. Okay, so using this particular method, let me just to show you, this is how it looks like. Okay, so we have a copper, we have this is the kind of roughening method. Okay, and then we are able to achieve a relatively very good adhesion. Okay, so let me show you this picture. So you can see that in this picture here, okay, that this is a glass sample, okay, and this is also a glass sample, and you can see that on certain area, certain specific location, okay, you can see that this is a rough, this is also a little bit kind of rougher area, and you can see that in the shadow, okay. So what will happen here on these locations, this and this location, the adhesion of the electroless film is going to be much better. Okay, so if you want to see, I mean, we have done a lot of experiments to find out that what kind of surface roughness is desired, how we can play around with the surface roughness, what are the critical parameters and all those things. Okay, so by changing the size of the rigid particle, okay, as well as the USM power, okay, we can basically create various kind of roughness area on that particular part. Okay, and if I go ahead, okay, so you can see that this is the same glass sample, but you can see that now we have electroless nickel. Okay, that's why the color is changed here, right? And if you look at the zoomed view of this electroless nickel, okay, this is how the electroless nickel look like. Okay, this is particle size is going to be very, very small. Roughly thickness of this particular electroless nickel can be varied from 20 nanometer to 100 nanometer plus. Okay, and once you have this particular sample with electroless nickel, please remember that the electroless work as a seed layer. It means that if you connect with the power supply now, okay, you will be able to deposit some kind of a metal. So that's what has been shown in this picture, right? So if you look at this picture here, 0 second, okay, this is nickel. And when you look at 5 seconds, so we are providing the, current from the top side. You can see that slowly, okay, the entire part, you can see that this is the copper is being deposited on the entire part. So within 20 seconds, okay, the entire electroless nickel layer is covered with electroplated copper. Okay, and electroplating where we are applying the external power supply to do that. Okay, this is how the sample basically this looks like. Okay, so you can see that entire part of the glass sample now it's going to be covered with the electroplated copper. Okay, and if you look at the cross section picture, this is some of the results. So blind vias, you can see that even the blind vias, okay, we are able to deposit the electroplated copper. Okay, so this was the picture with electroless first, then after electroplating, this is how it look like. So one of the challenge for us to find out how to make sure that the electroplated film, okay, is being conformal, is a continuous film. That was one of the major challenge for us to find out. Okay, and by the careful planning and experiment, you can see that. Okay, so even in, for example, 1 millimeter thick glass sample, okay, you can see that copper is completely deposited here. You can see that all the side wall, okay, it is covered by the electroplated copper. Okay, it basically means that the electroless seed layer was kind of a continuous, and then you can use it, you can completely fill this kind of vias by electroplated copper. Okay, so that is one of the kind of major result from our us. And after that, okay, you can see that the first objective which I had indicated in the beginning of the lecture, okay, this was our objective, and we were able to complete this kind of objective here. So you can see that this is the some picture during the process. So first we created this kind of spiral structure. Then on the center part we have created this kind of through hole. Okay, and then this one line basically indicate on the back side. So I hope that all the faculty members are able to correlate the design thing to the actual results. Okay, so after making this kind of vias, electroless, electrolytic plating, we are able to achieve. So this was the actual sample of the spiral inductor which what we wanted to fabricate. Okay. Now the basic thing, basic idea is that, okay, this is just one design. If you want to have any other design, in principle, whatever design which you have, you are able to do that. Okay. Similarly, these are some of the new results. Okay, even in case of alumina. Okay, so this is how alumina looks like. Okay, white thing. You can do electroless. You can do electroplating. This picture basically indicates that the electroplating copper is going to be completely uniform. Okay, you can see that this is, if you look at this picture here, you can see this alumina, and this slightly whiter picture is about the alumina. Okay, so even in case of alumina samples, okay, we are getting some kind of a good results. Okay, so same thing is shown in another centered alumina and so on. So idea here is that if I basically summarize my overall talk, okay, that these results which we are showing, all these materials, whether it's a glass-based sample or silicon or alumina, they're all basically brittle materials. And even in this brittle materials, we are able to create these kind of microstructures. And then we were able to demonstrate some of the basic application in the semiconductor packaging part here. Okay. So if I summarize my overall talk, okay, The first thing is which I wanted to highlight here is that this particular domain of semiconductor packaging is extremely important for India. Okay, government is putting a lot of interest in this particular domain. We already have more than 10 plants which are already announced, and another I think 6 to 8, 10 plants are going to come in near I think couple of years. Okay, and these are semiconductor packaging plants. Once these plants start working, okay, we will have at least 50 plus companies which are what you call as a supply chain companies, right? For example, companies like Corning Glass, Asahi Glass, Shot, okay, they're also going to come in India. So for example, you might have heard that Tokyo Electron Limited, they are going to open up two centers, one in Gujarat, okay, another is in Bangalore. And Tokyo Electron Limited basically is the manufacturer of the equipments which are going to used in this particular domain. Okay, so as a academic professors, we have basically we have to put some efforts in this particular domain. Second thing is that, okay, even the mechanical engineering students as well as faculty member, they are going to be very, very important for this particular domain. Okay, however, we need to slightly change our focus. Okay, we need to think beyond metal alloys. Okay, we need to think also from for polymers, because polymers, ceramics, brittle materials, they are also going to be very important thing. We need to develop the new techniques to create the micro features in this particular domain. Okay, so right now we can demonstrate it, but industry wants the process which has to be less than 50 micrometer. So how to do that? Okay, right. So, but if we want to basically develop the skill set, then we need to train our students in this particular domain. Okay, so the process like laser process, laser assisted chemical etching, ultrasonic, they're all going to come in picture and so on. Okay, that is very, very important point which I want to highlight here. Okay, so let me stop at this particular moment. I have about 10 minutes, okay, to answer your questions. Okay, so let me see if I have any questions on that part. What is the voltage? Okay, so I can see this question. So Nitesh Krishnan has asked this question. Okay, what is the voltage range in the case of ECDM? Okay, so critical voltage basically required in ECDM process depends upon what kind of electrolyte you are using it, what is the concentration of the electrolyte. Okay, so typically for a KOH electrolyte which we are using it, the voltage has to be more than 40 volts, right? If you go for a higher concentrated KOH, okay, then voltage which is going to become. Okay, so typically range is going to be 40 to 70 volt is going to be the voltage range which is used in the electronic in ECDM process. Okay. Any other questions, Piyush ji? Any questions from the audience? You can write down those questions on the chat box.
Participant, any questions?
All the faculty members who are working on the field of mechanical engineering, I think you can speak up, right? You might have some few questions based on whatever I had covered so far. Okay. If you are uh, interested in knowing about our equipments, you are more than welcome to visit IIT Bombay. I would be happy to. Yeah. So yeah, Nitesh is asking question about magnetic field effect. See, magnetic field effect is not going to have a very drastic effect on that particular part, because as I said, okay, that in ECDM, okay, uh, it is the material removal is mainly affected by the chemical assisted etching. Okay, so as long as you can increase the temperature on the surface, okay, you can basically do that. So, so electrolyte concentration is going to be very critical part. Okay, the voltage, higher voltage is going to be influencing. The gap is going to be the critical part.
डिस्कनेक्ट कर जाओ तुम।
Yeah. Okay. So Mr. Yeah, Mr. Venkatraman is asking question on how this technique is better than using ultrasonic abrasive machining. So are you referring to ECDM? So if I look at ECDM versus ultrasonic, right? So ultrasonic, for example, is definitely better than better in case of drilling, because in abrasive, if you look at, for example, if you look at my hand, right, ultrasonic is vibrating in the z-axis, correct? Okay, so if you want to create any kind of holes, ultrasonic is much better. Okay, but if you want to create, for example, any kind of a channel formation, right? So now yeah, so for channel formation, our experience is that ECDM is better, because in ultrasonic what happened, that vibration is in the z-axis, right? But if you have to move in xy, so you need to have some kind of optimized value. Sometimes if you are having a very fast speed in xy, then you may not get a kind of channel very accurately. So what we are saying that, okay, for drilling point of view, is ultrasonic is definitely better. For channel formation, ECDM is better. Okay, first thing. Second thing is that whether this method consumes more energy. Of course, ECDM basically involves voltage. Okay, so we have not done any kind of a very calculation on the power efficiency and so on. Okay, but definitely, okay, all both ultrasonic as well as the ECDM, they are non-conventional machining process. So it means that compared to conventional machining, they are maybe not be enough. Okay, how much depth we have achieved in glass machining? So glass machining, we have gone up to 3 mm thick. Okay, even by ultrasonic micro machining process, 3 mm, 4 mm we can etch, no problem. In case of ECDM, we have only gone up to 1 mm, because when we use the multi-tip, okay, removal of the sludge becomes a bit more challenging in case of ECDM. Okay, so one of my current student, he's working on his combined ultrasonic and ECDM both together. What will happen when using electrolyte? Okay, no. So ECDM cannot, in ECDM we cannot use any dielectric. The basic fundamental of ECDM is that the first stage of ECDM, you have to achieve electrolysis of water. It means that you have to produce hydrogen gas film. Okay, it means that you have to use some kind of water-based electrolyte. Okay, you cannot use dielectric in case of ECDM. Okay, it has to be electrolyte, and if you talk about ECDM, it has to be alkaline electrolyte. Yeah. Anybody else has any questions? Those who are nearby Mumbai, okay, I would like I said, okay, if you're looking for some kind of a joint supervision or some kind of collaborative work, okay, please contact us. We are more than happy to, help you out in that way.
Okay, so there is no further questions.
Yeah.
Then let us end come to the end
Yeah.
of
So
this session. So thank you very much, Dr. Pradeep Dixit, sir.
sure. Okay. So, and yeah, I have just shared, because sometimes, okay, both my email as well as my number I have shared. Okay. So in case somebody would like to speak, okay, you can basically message me on this particular site. That's not a problem. Okay.
Okay, sir.
I think PUC, that's from my side. Okay. Thank you.
Okay, sir. Thank you.
Thank you very much.
Have
Yeah.
a good day, sir.
Thank you, sir. Yeah. Thank you.